The next machine learning algorithm that we're going to cover is the decision tree. It is a very straightforward algorithm and it's very commonly used in machine learning. It is basically a classification or regression technique. It is a subcategory of supervised machine learning algorithms, and it is very well suited for situations where the relationship between the features and the target is not linear. And one of the advantages of it is that you can very easily visualize it and convey the findings of a decision tree within a beautiful, beautiful chart. Now, the best way to think about the decision tree is to go through the game of the 20 questions. And if you need a refresher, the game of the 20 question is designed so that you can guess a unknown person, place, or a thing using only 20 or fewer questions that can only have a yes or no answer. So on the right-hand side of the screen, I've created a decision tree that represents a simple game of 20 questions. You start with, say, a question. You're asking whether this thing that you're thinking about is alive or not. And suppose that they say, yes, the person is alive. And they say, okay, is this a person or an animal or a thing or a place? And when you ask, is this a person? If they say yes, then you can go and say, okay, is this a friend or no? And they say, no, it's not a friend. Is the person in the family? Yes. And then it's got to be easy. Is it dad? No. Is it mom? Yes. So you can reach the conclusion and figure out who the person is through a iterative sequence of smart questions. And if you play this game, you would know that it is very important to ask the right questions and in the right sequence. So decision trees implement such a strategy, but as humans, we kind of know how to ask these questions, but how does a computer figure out what is the best question to ask? Well, before we answer that, we have to know two concepts. The very first one is the concept of entropy, and it is a measure of the randomness in the data. The higher the entropy, the more difficult it is to draw conclusions about from the data. And an example of a data set with high entropy is flipping a coin. When you flip a coin, it can be heads or it can be tails, right? It's 50-50. You cannot make any conclusions about the results before flipping the coin. Specifically, if the coin is a fair coin, meaning that there is equal chance of it, coming out to be tails or heads, right? So for flipping a fair coin in which there is equal chance of heads or tail, you're dealing with a situation which has a very, high entropy. So let's visualize this concept. If I flip this coin, you don't know whether it's going to be heads or tails, right? There is equal chance for it to be heads or tail. Now, if this coin was a rigged coin, as this coin it truly is, it's on the riggedcoinflip.com, then you would know the result of the flipping before doing it because it's a rigged coin. So specifically in this example, if I click on the right, it is always going to be tails, whereas if I click on the left, it is always going to be heads, right? So if I say flip this coin a million times, and on all of those million times, I always click on the right-hand side of the coin, it's always going to be tails, right? So in this particular example, where the coin is rigged, then the entropy is not that high, it's lower, right? You can have an idea of the results before conducting the experiment. We can show that through a mathematical representation, which I will go through it, and a very nice chart. So here you can think of entropy that is going to be between 0 and 1, And let's say that this is about flipping a coin. When it's a fair coin, meaning that the probability of, say, an outcome is 50%, equal chance of it being, heads or tails, you would have the highest level of entropy, right? The highest level of uncertainty. Whereas when the coin is rigged, as in the example that I just showed you, where say the probability of it being heads is always 100%, then you would have the lowest level of entropy here, which is equal to 0. And the equation says that entropy is equal to the sum of negative p multiplied by log of p in the root of 2. And I'll show you how to calculate it in a second. So let's say that we have flipped a coin for 100 times, and in the case that it is actually a fair coin, out of those 100 times, we had heads for 50 times and tails for another 50 times. Now, if you plug in its formula, you would have to you have to first calculate the PIs for each of the outcomes. So the probability of heads in this particular case is going to be 50 over 100, which is equal to 50%, and the probability of tails, or P2, is also going to be 50%. Now, if you plug in this formula, which is going to be negative 0.5 multiplied by log of 0.5 minus 0.5 multiplied by log of 0.5, you can get the result of 1. And just so you see, I just plugged in Google Calculator, and this is what you get. Now, if we had a rigged coin in which the probability of receiving heads was of getting heads was 80%, whereas tails was only 20%, you would be able to plug in the numbers, and you'd see that the entropy would be 7.72, right? So when you compare the entropy here is 1 versus 72, you'd see that the entropy decreases, meaning that your certainty increases. Why? Because when you have a rigged coin, the chances that you can predict the outcome is going to be way higher than when you have a fair coin. Okay, the second concept that is very closely related to entropy is information gain, and it is a statistical measure for calculating how well an attribute separates the data, right? It basically is the difference between the entropy after you have done a split based on a feature versus the entropy in the dataset before you have done the split. In other words, the better the feature is for you to determine the outcome, the higher the information gain is going to be. So if you want to decide, which feature to choose for splitting the data set, you should see how much of information gain you would have as a result of that particular splitting. So when there are, say, two candidates for splitting the data set, and one of them gives you a particular information gain, the other one gives you another level of information gain, you should choose the one that gives you the highest level of information gain. Now that we know these two concepts, we can talk about one of the many algorithms for decision trees. A famous one is called ID3, or Iterative Dichotomiser. The way that it works is that it starts with the original set, calculates the entropy for all the features, chooses the one that gives you the best. What do I mean by the best? It means that the one that gives you the lowest entropy or the highest certainty, right? So I had a typo here, I had the highest, but it should be the lowest, right? It gives you the lowest entropy, it means the highest certainty. And once you do that, you would be left with S-1 features. And then to choose the best feature among them, you would again calculate the entropy for each of those splits. And based on that, you calculate the information gain, and you would see which one gives you the highest information gain, and that would be the one that you would do your second split. And then you go to the third one and basically repeat these steps, choosing the feature to split based on the highest information gain that you can possibly have until you reach the maximum depth of your tree, or you are gone through all the possible categories that you can split your data based on. That is when the algorithm is going to stop.